Now, Gianni Barlacchi will talk about human mobility using machine learning. So, thanks to be here.
So, thank you. Good afternoon to everybody. I'm Gianni Barlacchi, and in this talk, I will try to talk a bit about what is human mobility and how we can set machine learning problems to deal with human mobility tasks. Okay, so a few words about me. I'm a computer engineering, and I'm doing a PhD in computer science at the University of Trento with a fellowship by Telecom Italia. I mainly work with machine learning models for natural language processing. And also I spend part of my time having fun with database. I hope some of you yesterday were here. We had the event yesterday night. We talk about data, and we have fun with beer after talking about it. So the presentation, as I said, there will be the first part will be an introduction to human mobility. Then I will talk a bit about mobility data, which is something that is not easy to find, mainly because there are many privacy problems behind. How we can characterize the human mobility, so how we can represent a user through its mobility, and how we can use this feature representation in a machine learning model. So at the end, some conclusion, and I will be glad to have some feedback also from you. The goal of the talk is to introduce this problem, show how to use human mobility data within machine learning model, and how to set the machine learning models to predict the next place location of our user. So, starting from a kind of definition of human mobility, when we talk about human mobility understanding, we want to know the law that are governing our motions. And usually long time and long distance trips are less frequent than short time trips. And when we talk about short-time trips, mostly they are about intra-city. So you move in the same city, and the movement is it consists of a few kilometers from your location to the next location. And human mobility is quite regular. So there are patterns inside that are that we can rely on, like there is a high degree of spatial and temporal regularity, and this allows us to use mobility data to infer something about the user and to infer something about what is happening around the user, like traffic and so on. And to support these things, this is this work from Gonzalez, Snyder, and et al., where they found that 90% of people can be described, the mobility of 90% of people can be described with 70 different network motifs. A network motifs is basically a network where each point is the place that you visit. So you start from home, you go work, then you go to drink a beer, and you go back home. So this is a three-place network. And the 90% of people, the daily mobility of 90% of people can be described with 70 different motif networks. So this means that basically there is a strong regularity in our movements. So human mobility can be divided in two parts. We can talk about collective human mobility, so we want to know the mobility of people, so the fluxes from one city to another, or between a region to another one. So we study the mobility from a collective point of view, and we can also study the individual mobility. So I can study the trajectory of the same user to understand something about that user. But why is important, and why we want to know something about how people are moving? Because from a collective point of view, is very important to understand the statistical properties that are governing our movements, because we can use this information for urban planning. If we have a region like now we are in south of Florence, we can understand from the mobility of the people that are living here that this is mainly a residential area, because people is leaving early in the morning this place and go back here late in the afternoon. So from a urban planning point of view, we can, for instance, use this information to design new park and so on, to understand how distribute new building in an area and so on. Obviously, traffic forecasting, because if we know the fluxes between places, we can also have a real-time idea of the traffic that we have in the road, and also a kind of migration analysis. And this is a work that I have done last year about refugees flows in a crisis region. This is just to give an example what means collective human mobility. We have the European region, and we know we had last year many refugees coming from Asia, Syria, and so on. The idea was to develop a software that can help a humanitarian organization to distribute people to help these refugees in the Balkan route. So the first thing to understand was how many refugees are arriving every day in the area, and we built a model, an arrival forecasting that was a time series forecasting model using the mobility of people, the mobility of people in the previous day to predict how many of them will arrive in the next days. Then, obviously, when they enter in Greece, they will move around the Balkan route. And so it's important to know the time in which they will visit every country, because if I have 1,000 refugees arriving today in Greece, I have to understand how to deal with them when they will be in Austria, because I have to maybe build a new refugees campus and so on. So there was a flow model that predict the flow of them, and a final exit forecast model that predict where they will go. So they arrive in Greece because they want to go in Sweden, they want to go in Germany, and so on. So this is an example of how can we use human mobility from a collective point of view. And just looking at the time series of arrival every day, we can see that they arrive in Greece, and the 6 days, in 6 days, they will reach Austria. This is 2 time series of the arrivals, and this is the autocorrelation between the 2 signals. And this is the best overlap between the 2 time series. And as we can see, is a quite strong overlap. So this means that they arrive in Greece, and it takes 6 days to move to Austria. And this is another example with Macedonia. They arrive in Greece, and in 2 days they will reach Macedonia. So just looking at the number of arrivals, we can infer the fluxes, the flow of them in the Balkan route. From the individual point of view, human mobility can be used to say something about the user, because if you tend to stay always in the same place, don't move around, you may have a kind of personality. If you tend to move around Europe, maybe visiting 10 different countries in a month, you may have another kind of personality. So mobility can say many things about the user, but we can also use individual mobilities for something like sharing economy. So we can track how people is moving around city to improve, for instance, the bike sharing system. So if I have to put in the city a new bicycle station, maybe I want to put the bike station in a place where I have more people and more requests. Also, as I said, mobility can say many things about you, and has been used in the credit scoring system. So how you move can say something, can reveal something about your reliability to pay back the loan to the bank. So they used the mobility of the mobility characterization of a user to combine it to other obviously information to understand if the user will pay back the loan or not. And can say something also about your health condition, because if you are getting sick today, maybe after work you go home, and instead of going to have a beer or going outside. This is an example of what we did in this last point. So we know the past mobility behaviors of the user, maybe let's say 2 days. So I know your movements from today to 2 days before. And the idea is, are you getting sick? So will you be sick in the next 2 days? So looking at your past behavior mobilities, I try to predict if you will present some flu-like symptoms, like a cold, fever, and others. And this information can be used in a machine learning environment where you have obviously the features, you have your target variable and all the steps, and the final goal is to say if you have or not flu-like symptoms in the next days. But this is something that is how to use human mobility for other purposes. Let's say how can we use human mobility to say something about your future mobility. Before that, I would like to talk a bit about mobility data. This is, as I said, something that is quite rare, because if you know the places where a person is, it's quite easy to recognize who he is, and from a privacy point of view, is not the best thing to do. The easiest way to collect mobility data is obviously through smartphone. Nowadays, there are almost 100% of coverage from the mobile point of view. So mobile phone is enable a massive data collection about the places that you visit. And how can we do with mobile phone? We can use the device, so we can install an application in your mobile phone, and we can track the movements that you do, or from the network. So telco operators, there is a distribution of antennas in a city, and when you connect to this antenna, the telco operator record that you connected to this antenna. So your position is like is the position of the antenna. It's not exactly the exact place in which you are, but more or less you are close to the antenna. So we have the GPS way, the wireless way, and the network way. All of these approach presents some pro and some cons, and obviously the wireless is the worst one, because it's quite easy to imagine that the data that you will collect through wireless will be very sparse, because you have wireless here, then maybe you move 2 hours around the city, you go in another place, maybe a Starbucks or some other places where you have free Wi-Fi and you connect to the Wi-Fi. But I have 2 hours of nothing about your mobility. So wireless is not the best way to do it. The best is with the GPS, but your battery will die in 10 minutes probably if we keep track of all your movements. So collecting data with your mobile phone from the point of view of the network, this kind of data is called call detail records. So this is the record that telco operator record in their database. Basically, they record the antenna, when you connected to one antenna, the event that you did, so who you call, and from where you call. And a CDR, how many of you knows about CDRs? Okay, so this slide is very useful. A CDR contains information about the event. So you sent an SMS, or you received as an SMS, you did a call, or you received a call, you connected to internet from where? Obviously, nowadays, internet is the most used thing from mobile phone. I don't know how many calls you received, but I receive more or less 1 or 2 days, two calls per day. This means that if we have to track the mobility using the places where you were when you received it, or you did a call, is worse than using wireless. But using internet, you are requesting information from an antenna every 15 minutes. So every 15 minutes, if you use 3G, 4G, or whatever, you connect to one antenna. So a record is registered in the database every 15 minutes. So it's a quite good segmentation of your mobility. And this is an example of standard CDRs. Obviously, every telco operator has its own structure, but this is the most standard information you can find inside a CDR. So, using a CDR, you can imagine that every antenna is used in an area, but this is a not deterministic situation. You may be in the D area, and you can use the C antenna. So the area, the area is defined with the most probable antenna. So you are in the D area, and the most probable antenna that you will use is the D. But it's not a deterministic thing. So this could create some problems, some errors in the data set. And when you move maybe from the first area to the second one, the third one, and you end up in the A antenna. And your location history is basically the ID of the antenna of the area that you visited. So it's necessary segment the space in squares that can be used to map your exact position, latitude and longitude in a square. And this is how we can do. This is Manhattan, and we can divide the area of Manhattan in many squares, and where each square is related to one antenna. And this in these settings is exactly what I showed you before. We know the ID of the squares, and we can convert the trajectory to a sequence of visited cell. Obviously, if I say to you, I moved from latitude 45, 300 to so if I move it to latitude 45, 300 to longitude 42, 6, I don't say anything. It's just a number. So you cannot infer, oh, see, yes, this was your home and you are going to work. It's not useful. We have to enrich the location information with something from the place in which you are. And we can do it with geographical data. Nowadays, there are many popular location-based social network that they have the description of a place, like Google Place. You have many commercial activities, and you have the description, the textual description of these activities. And also, you can use the official data that maybe the government collect with the census. The census data, in particular, contain a field called land use. The land use is the primary use of an area. So they have a shape, let's say south of Florence. The main use of south of Florence is a residential use. So we know that in this part of the city, people come here to sleep or to spend free time. This is a not updated data set. Maybe every 5 years they update the data set because it's very costly. It's a very costly operation. And to solve this problem, we can combine the census data with social network data, like, for instance, Foursquare. Foursquare provides API, and you can use this API to collect information about a venue. So you have information about the category of the place. This is a school, this is a police department, and so on. And once you have this information, it's very easy to have a general idea of what is happening in a place. To give you an example, this is New York, Manhattan, and this is the distribution of the point of interest in each square. As you can see, if obviously, if you don't know the distribution of the point of interest, for you each square is the same of another one. But adding this information, we can easily see that, for instance, the cell. We can easily see that the cell number 10 is a cell where professional and other places are predominant. This means that it's a place where there are many offices. So from an high-level point of view, just a distribution of the category of venues that you have in an area give you a very useful information. Also, if you use the land use information, we can almost find the same conclusion, because in the same cell, then we have the 5 category predominant, and the 5 categories commercial and office buildings. So now we can say, okay, in this part of Manhattan, we have many offices, and this is a commercial part of Manhattan. So if you are moving from here to, let's say, the north part of Manhattan, probably you are leaving work and you go home. And this is how we can combine geographical data with your trajectory. There are many challenges in collecting this data set, and in particular for the trajectory point of view, because I don't know about you, but I know about me. If someone tell me, I'm going to install an application in your mobile phone and I will keep track of your movements. No, thanks. Even if you pay 100 euros per day, probably I will not give you this information. Because it's something, the perception that people have about the places and the location where they are is very serious. I mean, I don't want to tell where I'm going to others, because it's something of very private. And I don't know, but probably most of you think the same. So the main problem is the privacy of the people. Well, who is working in this field often say, no, but it's very difficult to de-anonymize the user. It's a fake conclusion. It's very easy, because I know that you go home at 7 in a place and you leave this place at 7 in the afternoon of a place, and I know that you leave that place at 8 in the morning. So say, okay, this is the home. This is the home of this user. So de-anonymize the user is quite easy from this point of view. And then we have also to deal with missing or fake data, because in particular for the CDR, you have the position of the antenna. And in Trento, there is an area in the city center of Trento where the used antenna is the antenna in the Monte Bondone, which is the mountains in front of Trento. So if I'm going to see the data that I have about Trento, most of the users are in the mountains, in the middle of nowhere. So or they are all trekking lovers, or maybe there is something of wrong in my data. So there are problems. It's not so easy to deal with this data. But however, I want to give you some good data set in case after this talk you will fall in love with mobility data and you want to play with some data. There is this reality mining data set from MIT where they have information about 95 users for 9 months, and they not only have the location, but they also have the face-to-face interaction. So the user went around for 9 months with a badge, with a Bluetooth, and so they keep track also about the face-to-face interaction with other people. It's a very, very nice data set. And also there is this other data set, GeoLife from Microsoft, where they recorded, where they have the trajectory for 178 users for 4 years. And also this is very a very informative data set, because you can also see how the mobility of people changed during the time. Okay, so just to show how to deal with mobility and geographical data, I have here some pieces of code. And this is the first thing that you have to do is to segment the area. So you have one area, and you have to segment and create a grid over the area. How many of you knows GeoPandas? Okay. The pandas? Well, okay. So this is the perfect starting point. You have pandas, and within pandas you can use values, text, and whatever. When you have geographical spatial data, you have a shape. And a shape is basically a set of coordinates, latitude and longitude, very close each other. And if you draw a line between the points, you have the shape of an area. Obviously, it's necessary use something. It's necessary use some tools that can knows how to deal with this data. And this is a GeoPandas, which is a kind of pandas, but that allow that support the use of spatial data in the data frame. So you can load an area. In this case, I'm loading the shape of New York. And what we have is that we loaded the shape, and we have to transform the shape that we have, which is a spheric, in the spheric coordinate reference system, because the Earth is a spheric shape, we have to project from the spheric to a plane. And to do is very easy. Just say, okay, I want the unit in meters, and I want the reference system, which is 2236. But to do it, there is a website that says, okay, I'm working with New York. What is the number that I have to use? And you just put the number there. So this part is just to pass from a spheric coordinate reference system to a flat coordinate reference system. And this is the plot that we have. So this is the shape of the New York City. Now we have to create the grid. And to create the grid, the first thing we can do is to compute the number of squares that I can put in the horizontal axis and the number of squares that I can put in the vertical axis. And to do it, I forgot to mention, but in the first part there was meters 2000, so I want a square of 2 kilometers per 2 kilometers. So now I count the number of squares that I can put in the x-axis and the number of squares that I can put in the y-axis, and I just create, to do it, I use the boundaries of the shape. So this is my shape. I can get the smallest rectangle that contains the shape and work with the rectangle. Okay, so now I know how many squares I can put in the horizontal axis and in the vertical axis, and I can create the polygon. The polygon is a set of 4 points that define my square. That's it. And to create the polygon, I can get the first x point, and I can increment this of 2 kilometers for the next one, and so on. For each square, we have a centroid, because, okay, I have a square, but I need a latitude and longitude, because I need to map my trajectory here, and I can arbitrarily select the centroid of the cell. Now, it's important to have only the cell that overlap New York, because if I have a cell in the middle of the sea, for me, doesn't make sense. So we just do an intersection, as you can do a merge, as you can do in pandas, between the square that I have and the shape that I have from Manhattan. And I obtain a set where I have all the squares that overlap the Manhattan area, the New York area. Finally, I can add some other information to my record, like I will do with pandas. So I can say, okay, this is a polygon that stays in Manhattan, this is a polygon that stays in Brooklyn, so I can add whatever I want. And to create a geodata frame, I can just take the list of dictionaries, like I do in pandas, and I create a geodata frame. So the same exactly thing that you will do with pandas. And this is the result. So this is the shape of New York, and this is the grid that we created. Okay, so now let's move to human mobility characterization. And we have 2 dimensions, the space and the time. And we have our trajectory in this 2-dimensional space. To characterize human mobility, we can do it with a mobility trace. So a sequence of places that the user visited, where each place is the ID, that can be the ID of my cell, is the time, the arrival time in that cell, and the departure time from that cell, and the coordinate that could be the centroid of the cell. With this data, I should imagine some features, like I will do in any other kind of machine learning problem. Like I have a text, so from the text I can imagine the feature could be the sentiment. So the sentence is positive or negative, but also could be this sentence contain articles or verb or whatever. So the same approach I would use for a normal machine learning problem, or for a normal feature engineering problem. I can use the same approach here. And the one very common and useful feature is the radius of gyration. The radius of gyration quantifies the spatial stretch of your movements, of your individual trajectory. It's a kind of center of mass of of your movements. And basically, is the R is the coordinate. So latitude and longitude is a two elements vector, and RC is the kind of center of your trajectory, because it's the average, is computed as the n is the number of points. Very easy to calculate, to compute the radius of gyration. This is the data frame that we have, latitude, longitude, and data time, and this is the formula. You can just compute the RC like the mean, apply the mean to the latitude and longitude column, and then you can apply the individual radius of gyration, calculating the square distance between 2 points. Hertz distance is just a Python distance, a Python function that computes the distance between 2 points. So this is an example of human mobility feature that you can use in a model. This paper presents some very nice feature, but in general, the feature can be grouped in 3 different sets: distance traveled feature, movements, and visited placed feature. So to conclude this first part, we can say that human mobility is about studying the law of our movements. And to deal with trajectory, we have to segment the space as a first thing. And to characterize a human mobility behaviors, we can use distance, location, and other measures. And a good package to deal with this data is GeoPandas. If you have some questions, maybe one question, and then we can move to the next slide. Otherwise, we will keep the question for the end, as you prefer. Okay. Okay, as you prefer. Since there is a 45 minutes talk, I thought that was a good idea.
So you answered to my first question when you mentioned the data set from MIT, because I saw a project named Social Physics, and I saw it was quite in the same realm. And I was wondering if there is also some global project about human mobility, and if there is something that you are aware to understand better the behavior of humans or partners.
As far as I know, there are some data at the national level. At a worldwide level, as far as I know, no. In that case was a private data set, because this was a tool developed by from IBM, so there was many private things inside, and something that a normal developer can't use inside in a normal way.
Any other question?
Okay, I can
go on.
I can go on. Okay, now let's talk about how we can use the data in these machine learning settings. I spent the first part of the talk explaining the data and the mobility, because it's something that is not so common, like working with text or working with time series. This is the situation that we have. We have one grid, we have the points, and now the idea is, okay, so I know that you move from the first point to the third one, to the second one, and to the third one. Which will be the next cell you are going to visit? This is something that can be useful for all the tasks that I showed you before, but can be useful also to understand the life in the city, because we can imagine that there is an event and we want to know how many people are moving there to distribute the policies around, or mobility can be used to is actually used also to crime prediction. So try to understand the next movements of people is very important from this point of view. And as you may know, in machine learning you can do classification or you can do regression. In this case, if you do classification, you want to classify which is the next cell you are going to visit. And in this case, it's a multi-class classification problem. These are 3 references in case you want to go deeply in this approach, where they use a probabilistic model, neural network, and also Markov chain model. And also there is the regression. So I want to predict the number, the exact latitude, and the exact longitude. This is a very difficult problem, and also, in my opinion, not very useful problem if you're going to predict the exact latitude and longitude. And I will show you later why. So let's see the classification. And I thought that it was nice to see this probabilistic model by Calabrese and et al., where they basically try to understand your movements, not only looking at your mobility, but also looking at collective mobility. So we are in the Grand Hotel Mediterraneo. I know your previous mobility history, but I also know the mobility history of all the people that were here. So I can say, okay, you are going to one place, the probability that you are going to the cell 2 is 0.3. The probability that other people that were here moved to the cell 2 was, I don't know, 0.7 or whatever. So you combine the probability of individual movements with the probability of collective movements. So we are in the cell I, what is the probability to move in the cell J? So we have the grid, and for each cell in the grid, we have the probability that our user will move to that cell. Obviously, we will select the cell with the highest probability. And in the collective mobility probability, they also included information about land use and point of interest of the area. But let's see what we can do with neural network, since it's a very, very trending topic right now. So how neural network can help us with this problem. When you read a book, to understand one word, you probably use the information you collected through the process that lead you to that word. So you use your memory. With mobility, we can do the same analogy. So you have a sequence of places, which is it can be a sequence of words. And so to understand where you will go, it may be important to know from where in the morning you start, or from where, or the places in which you were during the lunch. So using something that can consider also the past information is very useful. One model is the recurrent neural network model that is that with this loop consider also previous information to say something about the present information. But in recurrent neural network, so the concept is that to connect previous information to the present task, and the loop can be seen as a sequence of layers. So you have the first block where you have the layers and so on. The problem of recurrent neural network is that the recurrent neural network is not good to learn long-term dependency. So let's say I want to go back 2 days in the past. With recurrent, you have problems, and there are very nice papers that can that you can read to understand this quite difficult problem. The solution is to use the LSTM network. LSTM network, basically the key idea is that you have the cell, and each cell weights the contribution of previous cell. So you can select what is more important in the past to go to predict your future output. And using this LSTM, we can try to predict the next place location with a kind of schema like this one. We start from the time and the cell that you visited, the sequence of time and cell that you visited. We can enrich this information with geographical data, and we can use these sequences in an input to an LSTM to produce the latitude and the final latitude and longitude. Here I reported increment on latitude and longitude because of the problem I mentioned before about predicting the right latitude and longitude. This is mainly because think about train a model on New York, and you try to tell to the model that if you are in Manhattan and you move to Bronx, you move from, I don't know, 40 latitude and 41 longitude to 40.001 latitude to 41.003 longitude. So you you train your LSTM with a very, very small range of number. And when you move to another city, you will ask to your model to predict the number that the model never saw, but also that these numbers are not connected in any way to the previous number. So obviously, probably you have to retrain when you change city the model, but the idea here is that you try to predict the increment that you have to put in the latitude and in the longitude. Because if you move from Manhattan to Bronx, you do, I don't know, 1 kilometer of movements. If you move in Rome, you can do the same movements, so the output could be, again, 1 kilometer. So it's a kind of trick to improve the generalization of the model. We can imagine one network with the easiest possible input, where you have the time and you have a representation of the cell. One easiest way to represent the cell is to use one-hot encoding. One-hot encoding basically is a vector where you have, we have in total 20 cells, and to select the first cell, you put 1 in the first element of the vector and 0 in all of the other elements. So it's a very, very easy way to pass from the idea of the cell to a vector, but this representation doesn't include any information about the cell, any information about the geography of the place, so it's like to say almost nothing to the network. So we can imagine some more interesting approach where we can try to create an embedding of the cell. Unfortunately, I don't have time to go in detail, but if you know about embedding and everything, we can talk later about it. So the idea of embedding the cell is based on the fact that if you see in a trajectory, many people pass from cell 1 to cell 2 and cell 3, you see cell 2 all the time you see cell 2 close to cell 3 and cell 1. And we can imagine to create a vector like word2vec where you have a kind of semantic representation of your trajectory. And this allow the network to better understand the context in which your cell is. A more complete input will be when we combine also geographical features. So we also say something to the network about the features that we have in this place, like land use, point of interest, and so on. This is the input, and how we can obtain our final output. Well, we have in input the latitude and longitude, and we want to know which will be latitude and longitude in the output. So we can get the increment in the latitude axis and the output in the latitude in the longitude axis, and we can sum, and we can obtain the new coordinates where you will go in your next movements. This model, classification and regression model, has to be evaluated. And the classification model could be easily evaluated with the accuracy respect of the cell. So my model, in the 90% of the case, classify the right cell in which my user will move. And this is a very straightforward way to evaluate a classification model in machine learning. For the regression part, we can use as a measure the distance between the point you predicted and the real point in which your user is going. So basically, it's just an error based on the distance in meters from the output of your network and the place and the latitude and longitude of your user went. Okay, so to conclude, in the second part, I tried to give an high-level overview about two possible settings, classification and regression. So you have mobility data, and you know that you can do classification, trying to classify the next square, or you can do regression. Obviously, the classification part is quite limited, because in the classification part, what you have is that your space is limited to the dimension of the grid. So you cannot predict, if you are considering only Manhattan, you cannot predict that your user will move to Manhattan, to Bronx, or to Brooklyn, or whatever. In the regression part, you don't have this limitation, but you have other difficulties because it's a more difficult problem. You are trying to learn, you are trying to teach to the network a more complex function. Then the geographical features can be combined as you would combine any other features with the trajectories of the user. And the LSTM represent a promising model that can be applied to this task, because this task, in analogy with the test, with a common text problem, is a sequence problem. So you can use the model that you use in many other tasks in sequence where you have sequence data in the mobility task, because you have sequence of information. Okay, thank you.
Yeah? Prova.
Hi. So first of all, thank you. It was a very interesting talk.
Thank you.
So you said that GPS data have a higher accuracy, but GPS data still are not very accurate. So for example, if you open Google Maps, you are here or there or somewhere else. So how do you treat this kind of data? Do you apply some filtering, some clustering?
Mm-hmm. Yeah, you can, well, depends from obviously from the GPS you are using. When you have, maybe with the GPS of a mobile phone, you have an error around, I don't know, 10 meters, 5 meters. I don't know exactly the range, but in my experience, I found this kind of error. To deal with this problem, there are some techniques like you said, clustering. So you can try to do, you can apply like the most common is DB scan. So you try to cluster many points to one unique point. And this is the same idea where you use the cell. You have one cell, you have many points inside the cell, and you map each point in the cell with the centroid of the cell. So a clustering could be one approach. There are some other sophisticated approaches when you also try to remove the places where you don't stop. So you have only the stop places. And in this way, you don't have maybe movements that are being registered randomly during your movements.
Any other question?
How do you handle trajectories that have a different number of points? Like, for example, I can move from here to the hotel, and maybe someone else, and you have to predict this, and someone else.
Okay. Yeah, you can use the same approach. So what is important is the place where you stop. So the idea is that you remove all the other points, and you only consider places where you stop. And the stop could be, in some cases, an hour stop or just stop that are where, how can I say, depends from the task. If you are interested to know where you live and where you work, for me it's important the stop that you do during the night or you do during the day. So the places where you spend more time, for me, could be the first places where you spend your time could be, for me, the stop places. So it depends from the task. You can define some rules to say, okay, this is a stop place or this is a not stop place, and remove all the other points. Okay, in the LSTM, for instance, you consider the you can consider, I don't know, the 6 previous movements. You remove. You just consider the time, and you say, okay, to me, I consider only the previous 6 movements in time from my user, and all the rest I don't consider that. In the case, for instance, of the probabilistic model of Calabrese, they use a time window of 1 week, and they divide it in hour. So they aggregate movements in hour, and they consider they consider 1 point per hour, and they consider movements in an hour, and they calculate the probability based in the time window of 1 hour. So it depends from what you are trying to do. Could be that you need more data, so you go back in the past, consider more points or not, but it's this kind of filter is based on the time.
Okay, hello. Are there cases where you have seen people using this kind of cell phone data to track internal migration within a city, to track, say, changes in land use or changes in population in different areas to predict demand for services? So, like school, children of a certain age needing a school in, say, 10 years. Are people using it like that at all, to track how populations might move in a given city or move from one area to another?
I don't know if I understood the point, but you have different kind of models where you have a matrix, origin, destination, and you just aggregate. The matrix is like one region or one city. Each element of the matrix is one city, and you have the number of people that move from the city here to the city here. And you can use this information, I don't know, for instance, this approach can be used to understand the spatial spreading of epidemics or whatever. Also the consumption of network, mobile phone network.
Yes, I
does it answer to?
Yeah, I understand that part. I've been working with a data science company, and we've been building open source models to track how land use changes in a given city.
Okay.
In particular,
okay.
London.
This is exactly what I mentioned before. They used the taxis, trajectories, combined to geographical data to understand what is the main use of an area, which is different from the use that you may find in the land use, because land use you have fixed categories like residential, commercial, and so on, but could be that in a residential area you have a very high level of nightlife, and maybe you can see this from the movement of taxi, that taxis are in this area during the night and goes in another area in the night, while you don't find taxis in the same area during the day. So this is something that changes in the time, because it could be that after a while they decide to close the clubs in this area and they move in another area. So during the time you can see this changing using some trajectories that can be taxis or people or whatever.
Sorry, a question. We saw that we can map the usually movement for a person, and we can predict the movement of this person based on other person that in the past make a similar track. I can use this kind of modeling also for predict unexpected event. For example, I know that I have a road with an important flux. I need to close the road. I can use this model to understand when person will go without have any past data.
I don't think so. In particular, this probabilistic model is based on what is in the training data set. So you just compute the probability of number of people that moved from that cell to this other cell divided the number of people. Regarding this approach, this is exactly what we did in the this is exactly what we did here. The goal of the flow model was, okay, Hungary is going to close the border, so where the refugees will go. So this was the goal, and more or less is the same. So there are other models like these flow models, that is a network model that try to estimate the probability that you move from a node to another one. And in this paper there are all the details, or we can talk later if you want. Sorry? Accurate. Accurate. I don't remember exactly, to be honest, because this was a demo that I did during my summer internship in IBM. They were working on this on this problem, and they tried to show that for humanitarian organization was important to have some software that support them in the organization of this on how to deal with this crisis. And this was done on the European crisis, so something in the past. I don't know if the main challenge here is that you have a new crisis, you use the same model we train here with data that we don't know what kind of data we have and what will happen. In this case, we don't know. In the case of this European crisis, the model was quite accurate in the sense that the error was less than 1,000 people, the worst case in the arrival time.
Okay. Any other question, or okay? The last one.
I think that these studies has an immense public interest, but as far as I understood from your presentation, the only ones who have access to the data to do something are the GPS service providers, such as Google or whoever, and the telecom companies like Telecom Italia, which is that you are working with. So, do you think there is a way to solve this problem, that this data has an enormous public interest, environmental and political interest, but the public cannot access it?
To be honest, I don't have an answer to this problem, because it really depends on the task. Because if you make available the movements, then companies could start to work with data to sell marketing. To the institution. It depends. Maybe in this, for instance, in this case of the humanitarian organization, you may ask to them to give you more data because you have a problem, a humanitarian problem that you are trying to solve. So in this case, the task is defined, and is for the in this for all the people around the world. So it's something that will help everyone. It depends. For instance, in the other work, this work with the mobility to assess your future health condition is a public data set that Telecom released to researchers to do this work. Even in this case, this could be useful for a hospital, because they maybe will know the amount of people that is getting sick, and they can maybe start some prevention activities and so on. But it really depends from the situation. To now, it's very difficult to access to mobility data.
Okay, thank you, Gianni.
Thank you.